Time we discussed the sequence-to-sequence or seq-to-seq architecture, where an encoder, that is an RNN, takes in a sequence, let's say a sentence, and compresses it to a fixed context vector. And a decoder, RNN, decodes this vector to a translation. We discussed several challenges that we had in this architecture. For example, we should wait for H2 to be computed to be able to obtain H3. So this means that we cannot really parallelize this computation, and we cannot leverage the full potential of our computational power in our GPU and TPUs. The other issue is, of course, the old issue of gradient vanishing and explosion, because of the fact that we are compressing everything in this vector and we take it with us. We try to take care of this with LSTM and gating, and we managed to do a pretty good job for short sentences. But of course, when we have longer sentences, the issue will still be there. So this gradient vanishing or explosion. We still have to deal with this if we want to go for a longer sentence translation, for instance. But the main problem here is really this fixed bottleneck that we have, and we want to continue from there. So here we will focus on this problem first. Okay, so to make this fixed bottleneck problem more clear, maybe in a translation task, let's look at the French to English translation. So here, for example, we have a French sentence and its translation in English. I want you to pay close attention to things that are making this fixed bottleneck assumption more challenging. For example, here we have this double negation pair that is not the case in English, right? That's one thing. The order of adjective, which is reverse in the two language. Coming back to here, for example, the second and fourth position that are really the same, is carrying the same meaning, should be coordinated, but we separate them in this. So we are asking RNN, base seq-to-seq, that somehow compress all of this structural information, word positions, grammatical dependencies, semantic roles, into this single fixed dimensional vector. But of course, when the sentence gets longer, this becomes more and more difficult. This is shown in the original seq-to-seq paper at 2014, where the authors show the blue score of the translation degrades for sentences longer than 30 to 40 tokens. Okay, so let's see how we can improve the situation or redesign the architecture to resolve this problem. C, and then we ask the decoder to decode from there. And once we compute C, we can throw away all of these computations. So one idea is, instead, each time when we decode, we look at all of these H's, right? So this way we are not really forgetting anything. We keep all of this memory bank or memory slots, and we access them to compute each decoder state. So now assume that somehow we are at the step or state T or ST of the decoder, and we want to compute ST plus 1, right? And here, what decoder does is basically first look at what we have generated so far, or ST, and it queries this memory bank, looks at each one of them to basically see what information is available. And then it wants to compute how relevant is this information, or basically where should I focus? Which ones of these HTs are the most relevant for this step of decoding? And then it wants to compute, let's say, an intermediate context vector, CT, that is an aggregation of all of these HTs weighted by their relevance. Okay, let's give it a different index. HIs from 1 to T at step T of decoding and weighting of that HI. So we want this weight to be normalized to 1 to basically have a way of pooling them. How can we obtain this dynamic context vector as opposed to previously fixed C? So basically we are looking for somehow a kind of lookup mechanism that the decoder wants to use to query this memory bank and retrieve this weighted combination of this encoder states. Okay, so this is very similar to the regression problem that we had. For example, we had xi, yi. Let's say we have n of them. And then the question is, what if I have a new x that is not in the training data? What is the y for that new x? The oldest way of doing it is if we imagine x's, for example, x1, x2, and x3 are somehow in this space, and we want to evaluate the value of a query, let's say x here. Let's call this query here. And we want to know how close this query is to this axis. So we can compute some form of distance, right? So let's call this distance here, distance between Q and X1. And if you remember, we compute the distance between two data points using some form of kernels. I'm going to use K here. So this is the distance between query Q and X1. This is Q and X3, Q and X2, right? And I call this Q, and let's call this f of Q, right? So we are looking to compute f of Q. Okay, so we said f of Q is a weighted value of this yi's, right? Because that's how we do regression. And these weights are computed using this case of Q and this x's. So since I want this wi to be normalized, I'm gonna use wi, which is a function of q, of course. Let's call this q from 1 to n. So wiq will be k of q and xi normalized by sum of all of these distances. So basically what we do here is just a kernel regression, right? So this way we will compute f of q, or the value of that query. So let's do some changes of naming. So here instead of yi, I like to call them vi's. Instead of xi, I want to call them ki's. I already call this q, and this is f of q, or the value of q. Now let's just choose a kernel here. For example, the Gaussian kernel. And we can write it like this. K of q and x is an exponential of some kernel bandwidth, q minus x 2. So we can visualize this, of course, so let's say in a one-dimensional case. For q here, we look at the distance, of course, from q to this axis. And then we weight this distance with this kernel function, so which has this form of Gaussian that we write it down. And we do this pooling based on that k, and that gives us the value of q for that q. We are connecting this to what we were discussing, that we want to basically see the weights to tell the decoder how much we want the decoder to pay attention to these previous HIs, which is somehow a similarity-based weights. So in that case, going back to the RNN state, what is the KIs? The KIs will be basically the HIs. The VIs are also the HIs. And the query was the ST, and the value of the query is SCT, right? So we use the similarity between ST and KI, let's say using this kernel mechanism, and we find these weights and we pool all of these values with those weights and compute CT. The result of that, so instead of f of q here, we call it attention of q, and here, so I had k here for the kernel and k here for the value, for the keys, because I'm not going to use this kernel anymore. I'm going to use alpha, if you remember. I'm going to call k as the vector of all of the keys, and v the vector of all of the values. Okay, so that will be the basically sum here. So I'm just rewriting this in this new nomenclature. So alpha I of q and vi from I1 to t. Okay, so how we are computing the alphas, just basically very similar to what we did in kernel regression. And we need a function that is taking in all of these weights or kernels that we call here A, and we want this to be sums up to 1. We already have that function, and that's softmax. So this gives us the softmax of for I. This is basically a normalization. Just to make it more explicit, this is like AQKI is somehow the log of the kernel here. This is like basically working in this log space is just computationally more convenient. We can use gradient descent to optimize A directly, and exponential in softmax converts this learned scores back to the proper probability-like weights. Okay, so let's review what we did. We had this fixed kernel, just like the kernel regression, that we basically handcrafted, like this Gaussian kernel. And we use this Euclidean distance, and we find this attention scores based on that. And here the question is, well, what if that kernel is not the best kernel, right? So we can do what we did before. For example, in the case of convolutional neural network, we learn the filter or the kernel there. Here we want to learn this kernels also. And if we do it, we basically have an attention mechanism that is learning the kernel and finding this relevancy between the state of the encoder and this set of all of these states in the encoder. So we are trying to compute the similarity between ST and HI, like we discussed in the case that we have the kernel fixed. Here we want to learn that. So instead of computing the similarity from the get-go, we first apply like a linear neural network. So weight matrix over S, and then a weight matrix over HI, and then some activation, let's assume tan hyperbolic, and then let's call we have to weight this also. That is basically like a scoring vector, and this will give us this score. Okay, this is known as additive attention, and it's the first time that the concept was introduced back in 2014. So in the next video, we will talk about this, and also we discuss another variant of attention, that is the dot product attention, trying to do the same thing, but in a more computationally friendly way.